So logarithms are inverses of exponents. All right. And so if we start with kind of like y equals a to the x. So if we start with an exponential, we'll call this exponential form. All right. The idea there, right, is our variable. So a would be a number, right? A would be a number, and then x is our variable there, and then so is y, I guess. But x is in the exponent. Our variable is in the exponent. Okay. So exponential form. Everything written in exponential form has an equivalent logarithmic form. So these two things I'm about to write here are equivalent. Okay. And so it would be log base a of y equals x. Okay. Log base a of y equals x. Okay, and so that's like how we would read this, by the way, too. So this is, you know, log base a of y equals x. Just so you kind of have that down, right? That's like the way we describe that thing. Log base a of y equals x. Okay, so you can see here that there's some kind of, you know, familiarity, right? For example, like a, remember, in the exponential form, a was the base, right, of that exponent, right? A to the x, the big number, right, is called the base. The x to the power here is called the exponent, or the power, I guess. So a that was the base here, now it is the log base a. So that's still kind of a base. All right, you can kind of see here that then the x switches over to the other side, and then y, the y kind of flips places there with the x bit. Okay, but that's the idea. That's what it creates for us here. Okay. So these two things are equivalent statements, equivalent things. All right. So let's take a look here then at an example about like how we actually use these things, right? So enough of that kind of abstract stuff. So how can we see that? So for example, okay, let's say we have log base 2 of 8. And let's say, I guess I should put in something here. Let's evaluate, okay, or you might say simplify, depending on your directions there. We're going to evaluate or simplify there log base 2 of 8. Okay. And so the way we want to solve this, the way we want to simplify this is like, I don't know what that equals, right? Like a lot of us probably look at that and like, I have no idea how to do that. So let's say it just equals some value x that we don't know. All right? And again, that doesn't really help because we have no idea what that is potentially. But we know that if this is the logarithmic form, the equivalent exponential form will be 2 to the x equals 8. Right? It was log base 2, so 2 becomes the base of our exponent. Okay, the a gets raised to the power x there, so 2 to the x, and then it equals 8. The y is the 8 there. Okay, so the 8 and the x kind of switch sides. The x becomes the exponent, and the 8 is what we're equal to there. And so now at this point, it becomes very easy, right? So x is what? 3, right? And so we can say that log base 2 of 8 is equal to 3. Log base 2 of 8 equals 3. Right. So the question, or kind of like the thing or the work that the logarithm is really asking us to do here, okay, so like in this logarithm, for example, okay, so when you say log base 2 of 8, okay, is asking 2 to what power is 8? Okay, that's kind of the work that the logarithm is asking us about. When you say log base 2 of 8, okay, that thing, that value, log base 2 of 8, whatever that value is, it's really saying 2 to what power is 8. That's what a logarithm is saying. 2 to what power is 8. Okay? That's what that logarithm is saying. So, with that in mind, let's evaluate some more. Okay? So, for example, let's do log base 3 of 81. Whoops, I'll scoot that up some. Okay. Log base 3 of 81. So we could ask ourselves the question, okay, so just like here it was 2 to what power is 8, the similar question here is 3 to what power is 81? Okay, well that was from our warm-up, and what was the answer for that? It was 4, right? So the answer here is 4. Okay, answer here is 4. Alternatively, right, if you're not comfortable with that, you could just do, okay, log base 3 of 81 equals x, we don't know what it is, and then rewrite this logarithm in exponential form. So it would be 3 to the x equals 81, and now maybe it's a little bit easier to see, oh yeah, x should be 4 here. The 3 to the 4 is what would give us 81 there. So x is 4. Okay, so either way there, you can do it. It's up to you how you want to do it. You can ask yourself the question, or you can do that. All right, let's try another one. Log base 3, so we'll say log base 3, but now we'll do log base 3 of 1. Okay. Log base 3 of 1. So what would this equal? Cassie? 0! That's right. How did you determine that, Cassie? Right, exactly right. Yeah, so log base 3, okay, of 1 is 0 because 3 to the 0 is 1. 3 to what power is 1? 3 to what power is 1? Well, it's 0, so that means this thing equals 0. Okay. Questions on any of that so far? All right. Let me throw another one at us here. Log base 4 of 2. Log base 4 of 2. So again, the question here, if we were to do the question, so here it was 3 to what power gives us 81? It's 4. Here we said 3 to what power gives us 1? 3 to the 0 gives us 1. So 4 to what power here would give us 2? Done? 1/2. Yeah, this is 1/2. Right? The square root of 4 is 2, so 4 to the 1/2 power would be 2. Okay, so it's 1/2. All right, do one more here. Together, we'll do one more together. Log base 10 of 1/100. Okay. So again, 10 to what power gives us 1/100? Cool. -2. Yeah, 10 to the -2 is 1/100. Okay. If you need to see that, right, we can rewrite it as like log base 10 of 10 to the -2, right? 1/100th is really 10 to the -2, and so that's just going to be -2 there. Okay. All right, let me give you guys something to try here. So you try log base 2 of 16 equals what? Log base 100 of 10 equals what? Log base x of x to the 5th. Okay, this one would be x not equal to 0. give those a try. Here you go. Thank you. You're welcome. All right. No clue? So you have you're not sure. Okay. No, I know. That's right. Yes. That was not the other two are. Very good. Okay, so this one is gotcha. Okay, I see. Yeah. Okay. Oh, okay. Okay, that was highlighted that way, but otherwise, yes. Okay. All right. Looks pretty good here. So let's see. So Anna, what'd you come up with there for the first blank? X equals 4, right, okay, 2 to the 4th is 16, okay, 2 to the 4th is 16, that's right. How for the second one there, Anna? 1/2, okay, yeah, 100 to the 1/2, or the square root of 100, right, is 10, so that's right. And how about that last one there, Anna? Yeah, 5. X to what power is x to the 5th? X to the 5 is x to the 5th, and so it's just 5, okay? It's just 5. All right. Question.
Does negative 2 and 1/2 take the same thing?
Negative 2 and 1/2 are not the same thing. No. So if this were negative 2, because the idea is, imagine if you do 100 to the negative 2 versus you do 100 to the 1/2. Okay. Negative exponents we saw yesterday was 1 over that, then to the positive 2, right? And then rational exponents like this, that's like the square root of 100. Okay. So not the same thing. Not the same thing. Okay? Does that clear up your answer there, Bayla? Does it clear up your answer? Does it clear up your question there, Bayla? Yeah. All right. So let's take a look at some other things here. We have some special logarithms, okay, that are named. They're so special, right? So for example, log base 10. Okay, it's known as the common log. Okay, and that's the logarithm that's in your calculator. All right. In the case of the calculator, it's the log base 10 is really the same thing as just the log button. So if you press just like the log button in your calculator here, you're actually doing log base 10. Okay, so that is log base 10. Even though it doesn't have a base there, it's log base 10. All right. So for example, if you were to type into your calculator log of 100, okay, if you were to type that into your calculator, remember that we would calculate it as log base 10 of 100, right? Because that's the same thing, log 100, log base 10 of 100, which would then be equal to what? 10 to what power gives us 100? Yeah, 2, 10 to the 2, so 2, right? And so sure enough, if you type in your calculator log of 100, you get 2. Okay, you can do log of 1,000 if you wanted to, or like 10,000, we'll say it's 4, right? You can do log of 0.1, which is 1/10, so you get -1. Okay, so it does do that, right? So there's that, and then we also have the, so there's common log, and we also have the natural log. Okay, and that is logarithm with base of e. Okay. So e is so special, it's called a transcendental number. It's irrational, like pi is. Kind of pi is also a transcendental number, I'm pretty sure. But e is kind of a special number, and we use e in a lot of applications. Pretty much every application that has to do with continuous growth. So, for example, population. All right, any population kind of growth is a kind of, you can model it continuously, even though technically you can't have like parts of people, right? Like you don't have a part of a person. A person is either person or not. So technically population is discrete, but just because there's so many, we just count it as continuous. Okay, you can use e to model that population growth, or likewise with like bacteria growth, or if you're talking about like the growth of money in a bank account, if it's compounded continuously, again you can use e. So e shows up in many applications wherever you have continuous growth. Okay. So and e is approximately, and this is going to be helpful for you guys in the future to know this, e is approximately 2.718. Just like, it's helpful to know that pi is about like 3.14, it's helpful to know that e is about 2.718. Just because, later on it will be helpful. Okay? So the way we write natural log, you could write it this way. Log base e of x, like this. But we don't write it that way. Okay? I'm going to guess that the French developed this because it's written like natural log, like a cursive L and N, and then an X like that. Okay, and this is the way that you write natural log. Okay. Okay. It's like logarithm natural. That's why it's like LN and not NL. Logarithm natural. Okay. It's the most French you're going to get in this class. All right. But it's just, you treat natural log just like you would any other logarithm, okay? It's log base e. Okay, so it's helpful to remember that. All right, anytime you see that, it's just really log base e. And that button is also in your calculator. All right, that is also in your calculator right down there, okay, next to the 4. Natural log, ln. Okay? So, there are some properties here, some 3 basic properties we're going to talk about, and then I'll show you some more properties of logarithms on Monday, virtually show you. Okay? So there's 3 basic properties that we're going to utilize just for today. Okay? So this is, let me see here. Yeah. Log base A of 1 is always going to equal what? Log base a of 1 will always equal what? Well, in other words, a to what power gives us 1? Yeah, 0, right? Any number raised to the 0 power gives us 1, except for 0. It's an indeterminate form. Okay? Right. Log base a of a is always going to give us what? So a to what power gives us a? A to the 1, yeah. And then one other property here. Log base a of a to the x will always yield us what? A to what power gives us a to the x? Yeah, x. Okay. So in this third property, you can kind of see kind of an indication here of that inverse operation or the cancellation kind of thing that I was talking about. Remember how I introduced, right, to you guys to logarithms in the first place? I kind of talked about them as being the inverses of exponents, right? So here you can see without the logarithm, I have an exponential, a to the x. But let's say I want to solve for x here. I can't like do the xth root or something like that. I need to get this x out of the exponent to be able to solve. Well, if I do log base a, okay, if I perform log base a on this thing, the log base a of a to the x is just x. Now the x I've taken from the exponent out, okay, to now be kind of something we can solve. Okay, so it's no longer in the exponent. We can now solve potentially for x. So that's the use, the utility of these logarithms, for our purposes at least, be to do that. Okay. All right. Let me see here. So yeah, I have one more thing. We're going to graph one logarithm here. Okay. So I also want to just graph a logarithm just so we can kind of see that. So we'll do, let's see, I think I wanted to do we'll do log base 2 of x. So we'll do one more thing, just graph a logarithm just to kind of see what they look like. Alright, so to do this, we're going to use a table of values here. And again, we want to be kind of choosy about what we pick for our x values here. Alright, we want to be kind of selective about what we pick for our x values. Okay. We want to be kind of selective about what we pick for our x values. For example, if I were to say like negative 2 here, if I were to say negative 2, that means that I would be doing log base 2 of negative 2. Right? Because the x, negative 2 is the x value, so it's going to go in for the x there. And to evaluate this, I would need to come up with some number. I would need to come up with some number 2 to some number that would give me negative 2. What exponent can we raise 2 to that exponent and get a negative 2? You're right, we can't. Okay, you can't do logs of negative numbers. I'll take your silence as we can. Right? Okay, yeah. Negative 2 won't work. So no negative numbers, for example. Alright, so we want to pick, though, numbers. So what would be a good number to kind of pick in here for x, though? What would be a good number, an easy number for us to evaluate? Because we don't have a log base 2 button on our calculator. So what would be a good number for us to pick here? 0, okay. Let's see here. Log base 2 of 0. So if I plug in 0, well, again, I want to figure out 2 to what power gives me 0. You're right, we can't. 0 doesn't work either. Okay, but Ellie, I think you were maybe onto something there. If we say 1, log base 2 of 1 is going to be what? Or in other words, 2 to what power gives us 1? 0. Now we finally have something we can use. So 1 gives us 0. Okay, 1 gives us 0. What might be some good other numbers to select here? Some other good numbers to select. Yeah, okay, powers of 2. Exactly right. Powers of 2 that we know. So yeah, 2, 4, 8. Okay, if you really wanted to go crazy, you could say like 1/2. You could say 1/4, because those are technically also powers of 2. Okay, powers of 2. So let's see here. Log base 2 of 2 is going to be, well, 2 to what power gives us 2? It's going to be 1. Okay? 4 will be 2, 8 will be 3, 1/2 will be to the negative 1 power, 1/4 the negative 2 power. Okay? So let's take a look at this now. Let's take a look at what this is going to be. Kind of funky. Alright. So all my x values have to be positive, so I'm going to worry about only graphing like the first and the fourth quadrant, because I also have some negative numbers there. So I'm just only going to graph the first and fourth quadrant. Mr. Mills.
What happened?
Just some logarithms. Yeah, it's good times.
I like it.
Me too. I don't know if they like it though, but you know.
Mama, do you like it? Wrong answer. They love it. I bring gifts.
Thank you.
Is this good?
Yes, perfect.
Enjoy.
Thank you. I will. I'm sure my algebra students will as well.
Oh, they always look like. That looks like an interest. Oh gosh. Love it.
Alright, so we'll just count by ones here. One, two, three. Okay. And so we'll plot some of these here points. It is important to use some of these fraction values, okay? Because our y values do actually get negative. You might assume if you only do like positive exponents of, the power 2 here in this case, so like, 4, 8, 16, so on and so forth, you might assume that it only, it starts maybe here at like 1, 0, and then just keeps going. But it does actually go below the x-axis, so we want to be careful about that. Let's see here, 4, 2, 8, 3, but then, yeah, 1/2 negative 1, and then 1/4 negative 2. Okay, so my curve is going to look something like this. Okay, something like this. Alright, that behavior, as we go to the left, as we approach 0, it's going to go down to negative infinity. So what do you think that maybe indicates? What kind of thing do we have here at x equals 0? What does it maybe indicate that we have there? Our graph kind of comes up to it, approaches it, but never actually hits it. So it's an asymptote. Yeah, we have a vertical asymptote at 0. Okay. Vertical asymptote at x equals 0. You can find the x-intercept, right? We know that already. We found it. It's just 1, 0. Okay. There won't be any y-intercepts in this case because, again, we have a vertical asymptote at 0 here. What would the domain of this be? What would be our domain here? Spence? Yeah, 0 to infinity. So not including 0 to infinity. That's right. And then the range, well, it's going to go down to negative infinity here, so we can actually say it's going to be negative infinity to infinity. Okay. One last thing I want to show you here, and then I'll get you guys started on your assignment. There actually is a way to graph this on your calculator, but I'm not going to show you how to do it yet. Okay? You're welcome. I just want to show you, though, visually, to compare two things, because I can't quite do it on my graph there that I have. So what I've graphed here is log base 2 of x, this guy right here. Okay. I've also graphed 2 to the x. And if I graph one more, whoop, no cheating. Okay. If I graph one more thing here, the line y equals x, how are these two curves related to each other? Kind of like transformationally speaking. How are those two related? Again, that's 2 to the x, and that's log base 2 of x. How does it look like they are related? Reflection over the line y equals x. If they're reflections over the line y equals x, that means they are what? Inverses. These two functions are inverses. So log base 2 of x and 2 to the x are inverses of each other, and so you get this reflection here, okay? Which makes kind of sense there, okay, about how these behaviors are kind of coming out, right? 2 to the x has a horizontal asymptote at y equals 0. Log base 2 of x has a vertical asymptote at x equals 0. Okay? So there you go. All right. So, any questions? All right, so your homework is going to be 2 problems out of the book and then a worksheet that I've got for you too here, just to get some practice evaluating logarithms. So from the book, it's going to be page 234, numbers 37, 39. And I'll give you guys the log worksheet too. So while you all are working on that, I'll come around and get your preferred countries.